So our last set of lecture slides here are going to deal with sections 12.5 through 12.7. I'm going to try real hard to get through all three of those today. Okay, so this 12.5 is about something called collision theory. Again, these should be numbered the lecture 7 slides. Collision theory means when we're talking about any reaction, a chemical reaction. Collision theory is saying these reactant atoms, molecules, or ions, if that's what we're talking about is ions, okay? These reactants, they must collide. In order to react. They got to physically what? Crash into each other. They got to physically collide. Okay. Here are some postulates. There's 3. You guys know what I mean when I say postulates? They're like the statements of the theory. Postulates means the statements of the theory. Okay. So there's 3 postulates for collision theory. Here's the first one. If we think reactions are caused by collisions, then the reaction rate, which we've spent 3 class sessions, I guess, talking about how to find a rate, right? The reaction rate is, you guys know what it means in math if I write that symbol? No. Maybe I need to write it a little more like that. Directly proportional. That symbol is means directly proportional. The rate of that reaction is now directly proportional to the rate of the collisions that are happening. More collisions happening, more faster, overall rate's faster. That should make intuitive sense. Guys, this is where it's super necessary. Guys, you really need to go back and review that section I told you to study on your own. The one about factors that affect the rate. Because every single one of those factors, pretty much that I can think of from that section, the reason they affect the rate is due to this thing called collision theory. Why do things need to be in the same phase to react more fast? Why does increasing concentration affect rate? Why does increasing temperature affect rate? It's all collision theory that we're learning today. So you really do have to go back, if you didn't already, review section 12.2, the factors. Okay. So more collisions means faster rate. But not every collision that can happen actually causes a reaction. Let me say that. This is color I'm going to use. Just use this color. However, not every collision of molecules Not every collision leads to a reaction. Sometimes molecules collide and there's no chemical reaction that happens. They just think about like in gas law, right? When the particles collide, they just bounce off each other. That happens sometimes. Why? Why do not all collisions lead to the chemical reaction? This is part of collision theory, okay? This is part of it. One reason is that in order to react, so I would check your messages, hun, because she's not going to be here today. And I know she talked to them about it last week. Yeah, she wasn't here Thursday. I mean, Miss Elena was here, but I know she talked to the class about what to do, so you need to check your messages. In order for them to actually react, the molecules have to be in the proper orientation. What does that mean? If I have a molecule of carbon monoxide, 1 carbon, 1 oxygen, and in this reaction, I'm trying to create carbon dioxide, okay? If the molecules collide this way, I'm not going to see a reaction happen. Look. If this molecule collides with my O2 molecule, oxygen to oxygen, that's no reaction. I'm just telling you that that's the case. I'm telling you this is what happens when sometimes things collide and there's nothing that happens. That's what's happening here. This and this colliding this way is not going to react. Do I expect you to necessarily know that? No, I'm just trying to make a point. They're not in the correct orientation, okay? But if this carbon monoxide collides with the oxygen this way, with carbon in the middle now, then we are going to get a reaction. What's going to happen? Now I made CO2. And now I just have what over here? I want to be sure you guys understand, in this kinetics chapter now, we will occasionally see oxygen as just the atom. We say atomic oxygen, okay? Sometimes that's a byproduct. Does oxygen like to be alone? Oxygen prefers to be diatomic or paired up with something. So while this may form, this ain't gonna hang around very long. It's gonna go do something else. Okay, but you might get this. You might see just an O. Okay. What did we see? One kind of orientation, nothing happened. The other kind of orientation, yes, a reaction happened. Not every collision leads to a reaction. Now here's the big one for today. Here's the big thing from collision theory that we learn. Molecules must have a required amount of what's it mean if I write capital K, capital E? kinetic energy. Okay. There's an actual amount of kinetic energy that the molecules have to have when they do what? What is this whole theory about? When they collide in order to react. When they collide in order to react. There's a required amount they got to have. It's unique for every reaction that could be. There's not a set value. Okay. It's unique for every reaction. We're going to investigate that. Why does it have to have a set amount of energy before they can come together? What are we actually doing when we do reactions? We are breaking. So IMFs are what we see during some reactions, during phase changes. It's why solutions would form. Guys, this is actually talking about true what? Not IMFs, true straight up chemical bonds, covalent bonds, ionic bonds, not IMFs, actual bonds. What is going to have to happen? We've got to break the bonds in the reactants. So that what can happen? So one more time. So the products can form their bonds. Without this amount of energy, these reactions never happen because there's not enough to break the bonds to allow new bonds to form. Without this required amount, a reaction will never, ever, ever, ever happen, ever. So what is this required amount called? This is what is known as activation energy. Activation energy. Activation energy is the minimum amount that's required. The symbol for activation energy is a capital E with a lowercase a subscript. Activation energy, the minimum energy necessary to form a product when reactants collide. Okay. If you don't have the right amount of activation energy, no collision in the world is going to form products. So what are we saying for a reaction to happen? What has to be true? First of all, everything's got to collide in the right orientation. Second of all, when that collision happens, they both have to have the right amount of energy in them. They are correct orientation, but not enough energy. Guess what? No reaction. What if they have correct amount of energy, but they're the wrong orientation? Guess what? No reaction. It's got to be both things. Can you see how that means not every collision is going to cause a reaction? What we're going to see is that we can tweak or adjust those factors right here, right? We can adjust factors to favor the number that will collide properly. Okay, we can do that. When we talk about activation energy, the way you will see this presented a lot of times is in what is known as a reaction. This is what I call it. Coordinate. Sometimes I think our textbook calls it just a reaction energy diagram. If you go on to organic chemistry, you see these a lot. In our coordinate diagrams, again, that's what I learned to call it. What we're going to look at is, I want y'all to sketch this. Okay, so we're just going to do an XY graph. Okay. None of what I'm going to draw is really going to be to scale. In fact, they're often not really to scale, but what we're going to track on our y-axis is the amount of energy. Okay. And on our x-axis, all we're going to call the x-axis is the extent of the reaction, or the progress of the reaction. Kind of like time. Like as time goes on, here's what's happening. But it's not a direct time measurement. It's just an overall, here's what's happening. Whenever you start off with a reaction, like let's just say I've got A plus B forms these two products, okay? Generic reaction. My reactants together have some amount combined of energy. Don't they? Didn't we learn that in thermochemistry? We can calculate how much potential energy total is there, or how much kinetic energy total is there. There's some amount of energy there. In chemistry, where is that potential energy stored? Like actually in the bonds themselves, right? So it's not potential like holding the bowling ball up off the roof, but there's potential here. Okay, you got some kind of sum of energy. When we draw these coordinate diagrams, what you will see is that these reactants are going to have some amount of energy in order to react and form products. So here on my coordinate, reactants forming products. Okay. The top of this hill, okay, the top of this hill is what is known as the, I'm gonna put a square bracket there, and then I'm gonna put this little symbol. Can y'all see? I know I'm kind of having to write small because I didn't give myself enough space. That's a line with two horizontal lines across it. That's called a dagger in chemistry terms. Okay. You see this symbology on these coordinate diagrams? Here's what it means. At the top of this hill is what is called the transition state. Okay. Here at the transition state is where you begin to transition from what? Reactants into products. Here is where what is true? Reactant bonds are breaking, so product can form. And what are the two conditions that have to be true for the reactant bonds to break? They got to be in the correct orientation, and they have to have the correct amount of energy for that to begin to happen, okay? Another word you may see, I can't remember if I saw this in your active chem homework or not. Here at this transition state, you end up with what is known as an activated complex. I wouldn't worry too much about that term. Activated complex just means it's when the reactants are joined up together and ready to do its thing. Okay. I would really just probably try to know, what are we talking about when we're at the top of the hill? The transition state, where it's ready to form product. Transition state. Okay. So what is this amount of energy called again? You guys tell me. What is this amount of energy that is required to go from where it starts to the transition state? That is what is known as the activation energy, that difference between reactants and the hill. Something else that's kind of interesting, I don't know how much we'll actually use this, maybe a little. Do you guys recall what's the difference in energy between reactants and products called? Very good. Delta H means change in enthalpy, right? What do you see happening in this reaction? This energy is higher than what we ended with. So final minus initial. What kind of number value, sign-wise, not value, what kind of sign number would subtracting, doing final value minus initial value give us? Yeah, in this hypothetical reaction, I would be getting a negative value. And what does that mean? It is exothermic. Again, that's just an interesting little side note. What are we focused on here today? This activation energy. Every reaction has its own unique amount of activation energy that it requires. Every reaction has its own. Oh, it's 100% matters what the temperature is. Wait a minute. Sorry. Let me rephrase. This value does not matter on the temperature. This value is the value for that reaction. Temperature can affect how fast the reaction is going to go, though. Okay. It is always going to be whatever this number is for that reaction. That's the number. This number is not going to change. What we can change is how fast we get over the hill. Getting over the hill is the rate. What's the slowest part of this process? Is it going up the hill or is it coming down the hill? Obviously, going up the hill is slower than going down the hill. Yes, obviously. So what is a factor that determines what the rate can be? From this concept, the factor I'm talking about is this determines what the rate is going to be, doesn't it? Doesn't it? What if you had this hill? What if you had this diagram? Let's sketch another one. Okay. Again, my coordinate is I'm just looking at energy versus extent. Okay. What if my reactants have, okay, this amount of energy together, potential before they start moving. Okay. And then here in this reaction, they have to climb a pretty big hill. Okay, what do I call the top of the hill? Okay, that's the transition state. Again, you could just see that word written. You could see this little symbology there, but that's the top of the hill is the transition state. Okay. So what's my activation energy here? Beginning to top of the hill, guys. This whole amount right here, activation energy. This reaction has a much bigger activation energy than this reaction, doesn't it? Which reaction, under similar conditions, Which reaction is going to go faster? The smaller hill, assuming everything else is the same, right? Temperature is the same between the two. Concentration is the same between. If I'm just looking at activation energy, obviously this one goes faster. Let me just show you what something that could happen here. What if you had this? Okay, what if, okay, now I'm ready to make my products. I've broken, now I'm forming, and the products made in this example have a combined final energy of that. What is this difference called again? That's the change in enthalpy, isn't it? Products minus reactants. This example of this coordination diagram shows what kind of reaction? This shows an endothermic reaction. Just because you have a big hill, does that mean it has to be endothermic? No, I could have had a big hill and then still drop down below the original energy level. Okay, don't let that get in your head. Okay. Yeah.
The activation is bigger than enthalpy, it's going to be endothermic.
Can't make that correlation. Enthalpy can only be calculated by looking at final minus initial, whatever those values are. You could have a huge activation energy or a small activation energy. That has no comparison. Okay. That is no correlation, I think is the word I was trying to say, right? Okay. Okay. How are we going to calculate activation energy? We got an equation. On your study sheet, it's the last three equations. Well, it's the same equation, it's just versions of it. Okay. It's called the Arrhenius equation. The Arrhenius equation. Arrhenius equation, or I think I'll shorthand this. I guess ARR. Okay, that'll be my shorthand. Arrhenius equation is now how we are going to relate K. What is K? Rate constant, right? With this new thing that we just learned called activation energy, with very obviously, I hope, temperature. Because this is all about having the right amount of kinetic energy. And kinetic energy is directly proportional to temperature. Okay. When we talked about a rate law, rate equals K, and then the brackets and the orders. What were we relating there? Rate to concentration. That was a rate law. What were we relating when we looked at the integrated rate laws? The relationship between time and really the rate constant K, but rate. And now we're looking at the relationship between rate constant and activation energy and temperature. You guys tell me what will happen if you increase the temperature, generally speaking. Just thinking in words, generally, if you increase the temperature, that means you're going to have more or less collisions. More. And you're going to have more or less collisions with the right amount of energy. More, because kinetic energy and temperature are directly proportional. You increase the temperature, they got more energy. So if you increase the T, the temperature, what should you see happen to your value of K? Yes, it also increases. What's that kind of proportionality called? Direct. Higher temperature means a higher K value. And just in general, that means what? A faster rate, right? Okay. And then we just talked about how rate can depend on the size of the hill, right? When I say the size of the hill, I'm being cute and I'm talking about what thing? I'm talking about activation energy when I say the size of the hill. The larger your activation energy is, the larger your hill is, and so the reason I'm writing it this way is because I can't actually increase the activation energy, right? The activation energy is what it is. So I'm not saying that I'm increasing it or anything like that. I'm just saying if this is what it is, if it's a large value or a very large value, what should I see about my K values? Small K values, smaller K values. The larger the activation energy is, the smaller that K value is going to be, which means what about the rate? Slower rate, absolutely. Cool? Okay. Equation. You guys will use this version and you will use the other two versions. So know all three. Okay. K equals A. Do you guys remember that letter A from chapter whatever 10? The Clausius-Clapeyron equation. You remember? I think I told you what A was, but I said we don't really care what it is. Here we kind of care what it is. A is what is known as a frequency factor, or what we use it to refer to is the frequency of collisions that form products. Okay, we're only interested in the collisions that are doing what? Actually doing the business. Okay, I don't care about all the other little collisions. So we're talking about how many collisions are actually happening that are making products. That's frequency. Natural number E raised to the negative activation energy divided by R times T. Activation energy is typically going to be kilojoules per mole. So that means what value of R do I want us to just automatically use? I want us to go ahead and use the gas constant in units of kilojoules per mole Kelvin. Okay. We're going to go ahead and use that value. And then, of course, what does our temperature have to be in? Kelvin. It's got to be Kelvin. Okay. What are the units of rate constant? What are the units of K? As it depends on the order of the reaction we're doing, doesn't it? Whether the units are molarity per second, inverse seconds, inverse molarity times inverse seconds. Yeah, it totally depends on the order. Okay. All right, the other two versions of this law, of this equation. Let's do this first. Okay, so here's our Arrhenius equation, right? Just like with the Clausius-Clapeyron, okay, I can take that equation and I can integrate it and get a linear version. If I integrate it, I'm going to get natural log of k equals negative activation energy divided by R times 1 over T plus the natural log of our frequency factor. Why is this called a linear equation? Because it's this format y equals slope times your x value plus the y-intercept. Y equal to x plus b, absolutely. So just like before, we're going to look at graphs and be able to pull information. Also, just like before, we have a 2-point version of the Arrhenius equation, which lets us compare what 2 points? Two different rate constants at two different temperatures, right? Two different rate constants at two different temperatures. So this format should look familiar to you from the Clausius-Clapeyron, right? Natural log of second constant over the first, that's how I choose to order, equals, when I order it this way, this value is positive, not a negative. And I multiply that by 1 over T, which one? 1 minus 1 over T2. Okay, good deal. Let's just, how are we going to find EA? That's an example I want to do before we take a break. So I'm going to show it to you right now. Okay. On your in-class examples, let's look at number 25. We're going to look at part of it using this equation, the 2-point. Okay. And then we're going to take a break. And when we come back from break, I gave you guys a graph. Everybody should have a graph at their seat. That's also about number 25, but we're going to look at it from a graph point of view and this 2-point point of view, which we're going to do right now. So let's look at 25. Y'all following everything okay today? Yes, y'all seem like you are. It's just because I'm so good. Do what, Loretta? Okay. All right. So you guys should have a table of data, yes? On 25. Am I on the right problem? Uh-oh, hang on. Oh, no, hang on. Maybe I got it wrong on my numbering. Hang on. Okay, that was 20. Yeah, how did I get off? Okay, it is 24. Sorry. It's 24, not 25. I don't know what I did. It's fine. You guys have this table of data, correct, Amundo? Cool. Okay, I have a table of data because I'm going to create a graph for the second part of this. But normally in a problem, you're just given 2 Ks at 2 different temperatures, right? Okay. You also are asked to solve for activation energy. If you have 2 Ks and 2 different temperatures and asked to solve for activation energy, what equation are you using? 2-point. 2 data points, 2-point form. And we're going to solve for activation energy. Which 2 data points are you going to pick just from this table? I gave you a little bit of guidance here since you do have a table to choose from. Choose the 2 furthest points from each other. So basically the first point listed and the second point listed.
Always.
I mean, I said the second. Last. First point listed, last point listed. If you're choosing from a table like this, always. You want the 2 points furthest from each other to get the best possible value. Normally, you guys don't have a table to choose from, but in this case, first and last. So what does that look like? What do you guys want to call K1 and T1? And what do you want to call K2, T2? Does it matter? Not really. I tend to put the lower temperature as the 1 value. I don't know why, I just do. You have to do that? No, that's just what I tend to do. So I'm going to say my first temperature is the 555 Kelvin, right? I'm going to do my lower temperature as my set 1. What does that mean my K value is here? Okay. 3.52 times what? 10 to the negative 7th. Guys, if you want to save a little bit of writing space to yourself, instead of writing, instead of taking up that much space, you can use what's known as calculator notation, right, Joseph? You can write a small capital E and then just the exponent, because that means times 10 to the negative 7th as well. That's fine. What are my units of K? Molarity to the negative 1st and seconds to negative 1st. That should tell you right away what order this reaction is. Not 0. Second order. Guys, y'all gotta know that. Y'all gotta know the units of K and the orders. Got to. That means this is a second order reaction. Okay. K2. T2. What if my temperatures were in Celsius? What would you have to do first? Convert them to Kelvin at 273.15. So we're going to use this last data set, 781 Kelvin and 3.95 times 10 to the negative 2. Okay. So I'm going to suggest for some of you that you may revisit my little strategy of letting all of that be what you're calling the letter A. And let this be what you call the letter B. And let this be what you call the letter C. Let that answer. So if you think A's, B's, and C's, if I'm going to rearrange for activation energy, I'm trying to get B by itself. So what am I going to do to both sides? Divide both sides by C, right? I'm trying to get B alone. So B equals A divided by C. Now, B is actually what two numbers over each other? EA over R, okay, equals A over C. What do I do now to get activation energy by itself? Both sides get multiplied by R. And now, you guys, find what A is. What are we calling A? The natural log of K2 over K1, right? Right. Times what? Up here on the top. Times R, right? What's down here on the bottom? What did I say is C is representing? What's here in this parentheses? Yeah. Guys, if you want to, again, save yourself some space, because I think a lot of us are more comfortable with this now. If you want to write this this way, inverse T1, because that's what this is, right? Minus inverse T2. You can do that. So we're going to take a break. You plug that in and let's see if you get my answer. Third. I'm sorry, I thought you said negative fifth. Sorry. Correct. Because we're dealing with activation energy in kilojoules, we're going to use that R value where we've already turned it into kilojoules by doing 10 times negative 3 times 10 to the negative 3. Yes. Yes. Okay. Here is my answer. And then, like I said, let's take a little break. And when we come back, we're going to look at a graphed version of this data. And this is rounded to have 3 sig figs based on, in our data table, our K values had 3 sig figs. Our temperatures, once they were converted to Kelvin, which we were given that, are 3 sig figs. That's what I would like for that, 3 sig figs. Okay. All right.